Welcome back, everyone. Spain is taking bold steps toward transforming its regional rail system by testing a new class of hydrogen-powered trains. These trains use onboard fuel cells to generate electricity from compressed hydrogen, emitting only water vapor as a byproduct. The initiative is part of a national strategy to eliminate diesel-powered transport in areas not covered by electric rail lines. Unlike traditional electrification projects that require extensive infrastructure, hydrogen trains can operate on existing tracks without overhead wires. Spain is collaborating with major rail manufacturers and energy providers to build, test, and certify these trains for passenger use by 2026. Field trials are already underway in several provinces with rural and mountainous terrain, where electrification is difficult and costly. The move toward hydrogen-powered rail could significantly reduce emissions and operating costs, while positioning Spain as a leader in next-generation transportation systems. Hydrogen-powered trains operate by converting hydrogen gas into electricity using a device called a fuel cell. This fuel cell combines hydrogen with oxygen from the air in a controlled reaction that produces electricity, heat, and water vapor. The electricity generated is then used to power electric motors that drive the train's wheels. Because the only emission is water, the entire process is clean and silent. This technology is especially attractive for rail lines that are not electrified, offering a low-emission alternative to diesel engines without the need for overhead wires or third rail systems. Spain's hydrogen trains will store compressed hydrogen gas in high-pressure tanks mounted on the roof or under the floor of the train. These tanks are made from strong composite materials that can safely contain the gas at several hundred bars of pressure. Refueling is done at dedicated stations equipped with pumps and safety systems that allow for rapid filling of the tanks. Each train can typically carry enough hydrogen to operate for several hundred kilometers before needing to refuel. This makes the system practical for regional routes and low-density lines. The core of the energy system is the fuel cell stack, a collection of thin plates that facilitate the chemical reaction between hydrogen and oxygen. Inside the stack, the hydrogen molecules are split into protons and electrons. The protons pass through a membrane, while the electrons travel through an external circuit, generating electric current. The electrons then reunite with the protons and oxygen to form water. This process happens continuously, as long as hydrogen and oxygen are supplied, allowing the train to produce power on demand. To ensure consistent performance, the fuel cell system is supported by a battery or supercapacitor that stores excess electricity. This auxiliary power unit provides additional energy during acceleration or hill climbs and captures regenerative braking energy. When the train slows down, the motors act as generators and convert motion back into electricity, which is stored for later use. This hybrid configuration makes the train more efficient and responsive, while extending the lifespan of the fuel cell by reducing load fluctuations. Spain's railway operators are modifying existing train platforms to accommodate the hydrogen system. These adaptations include space for tanks, cooling units, and control systems. The added weight and balance are carefully considered to maintain safe handling and stability. Engineers also upgrade onboard safety systems to monitor gas pressure, temperature, and leak detection in real time. Special venting systems are installed to disperse hydrogen safely in case of a malfunction, ensuring that passenger safety is never compromised. Refueling infrastructure plays a vital role in making hydrogen trains viable. Spain is working with energy companies to build hydrogen production and distribution facilities at rail depots and terminals. These facilities use electrolysis to split water into hydrogen and oxygen using renewable electricity. The hydrogen is then compressed, stored, and delivered to refueling stations along the network. Each refueling station is designed to quickly and safely service multiple trains per day, minimizing downtime and supporting high service frequency. Train operators and maintenance teams receive specialized training to handle the unique components of hydrogen-powered trains. This includes fuel cell maintenance, hydrogen storage inspection, and high-voltage electrical systems. Maintenance depots are upgraded with ventilation systems and safety protocols to manage hydrogen handling. Sensors and diagnostic software are integrated into the trains to provide real-time data on system health, enabling predictive maintenance and reducing unexpected failures. The control systems on hydrogen trains are programmed to optimize fuel use and coordinate power delivery from the fuel cell and battery. Advanced software balances the energy flows to maintain efficiency and performance under different conditions. Train drivers can monitor system status through onboard displays, receiving alerts if any values go outside normal ranges. These systems are designed to work seamlessly with existing signaling and train control infrastructure, allowing smooth integration into current operations. Environmental monitoring is also part of the hydrogen rail project. Sensors placed along the track measure air quality, noise levels, and emissions to compare performance with diesel counterparts. Preliminary data from trials shows a significant reduction in noise and local pollutants, which is especially beneficial for rural and urban areas alike. These results help make the case for expanding hydrogen train service and investing in cleaner transportation infrastructure across Spain. One possible future development is the creation of autonomous hydrogen trains for rural or low-traffic routes. By combining hydrogen propulsion with advanced sensors, GPS tracking, and artificial intelligence, these trains could operate with minimal human intervention. This would reduce operational costs and make it feasible to maintain regular service on less profitable lines. Autonomous systems could manage speed, braking, and refueling schedules based on real-time data from onboard systems and infrastructure sensors. Integration with regional scheduling software would allow these trains to coordinate efficiently with the rest of the network, while adjusting routes in response to delays or demand changes. Another development may involve hybrid trains that use both hydrogen fuel cells and overhead electrification. On electrified main lines, these trains would draw power from existing infrastructure. When switching to rural or disconnected lines, they would activate their onboard hydrogen systems. This dual power approach could significantly expand the range and flexibility of Spain's passenger and freight rail services without requiring full electrification of every route. The trains could also recharge their onboard batteries while connected to external power, increasing efficiency. This strategy would allow the same train to travel across a mix of electrified and non-electrified tracks without disruption. If these trials meet safety and performance targets, Spain's hydrogen trains could begin commercial service by the end of 2026. The trains are designed for quiet operation, fast acceleration, and long-range travel between refueling stops. Hydrogen refueling stations will be installed at key points along select routes, powered by renewable energy sources like solar and wind. In time, this network may expand to freight services and urban transit systems, creating a wider hydrogen economy that supports clean mobility across sectors. Spain's early investment in hydrogen rail aligns with broader European goals for climate-neutral transport and could serve as a model for other countries with extensive non-electrified rail networks. Thank you very much for watching. Please like and subscribe.